Testing, testing. Good. I can see the slide, Mary. Excellent. All right, we'll wait for people to get here and start.
Should I start?
Mary, wait a bit. How long is your presentation?
It's less than 25 minutes.
Yeah, we have a good amount of time.
Okay.
I don't know whether in-person people have returned from their lunch. I don't see Martin yet. And I guess we don't have a camera to look in to the room. And do we have any way to hear from people in the room? Is there anyone in the room? Thanks, Shay. Okay. We can start. So, Amir, let me introduce you first. So welcome to the second paper session. I see a good number of people online. Welcome to the session. So having a hybrid conference is not easy. I can't actually see in the room, but I think we do well because as SMM, we have shared interests and mutual support. I really like the morning sessions. I want to give my compliments to Michael and Martin for the well-run sessions. And I'm embarrassed to say that I actually had a conflict I didn't realize when I promised to chair this session. I just overlooked that 10-minute conflict. But Martin will, once he comes back, will be stepping in to take over the transition for the last two papers. It's just demonstrating again the mutual support we enjoy here at ISMM. In this session, we have three papers. We have half hour for each paper, so we have really plenty of time to clarify and discuss. If we need more time, we have a social break after this. So without further ado, the first paper is MemSweeper, Virtualizing Cluster Memory Management for High Memory Utilization and Isolation, presented virtually by Amiri Hossein Seri from University of Illinois at Chicago. Amiri.
Yes. Hello, everyone. My name is Amir Hossein Seri. I'm a PhD student at UIC, and I'm going to present to you our paper called MemSweeper, Virtualizing Cluster Memory Management for High Memory Utilization and Isolation. In this talk, we are focusing on memory caches that are a category of software caches that use the main memory of the system as the primary storage. So the application doesn't have to access the disk. Memory caches are very crucial in running web applications. For example, major web service providers such as Facebook and Twitter use them to handle high volumes of traffic. memcached is one of these memory caches which is used to reduce the load on backend databases and improve the latency of the requests. Databases are a critical component of web applications that are used to store and manage large amounts of data, but they cannot handle big volumes of requests quickly. So they require in-memory caches to filter out most requests. By servicing most requests from the main memory, the high hit ratio memory caches drastically cut the number of accesses to the disk, which would happen in case of cache misses. So caching solutions such as memcached or key value storage are offered by cloud providers such as Microsoft or Amazon as a service to customers who need a caching layer for their web applications. To achieve high utilization, cloud operators put multiple tenants or applications in the same physical machine. So all the servers resources, such as CPU, network bandwidth, and main memory will be shared between those tenants. This is the area that we are targeting. The multi-tenant environments, such as commercial clouds, in which a physical machine might host multiple cache tenants or applications. A recent paper from Microsoft discussed how cloud operators try to bin pack as many VMs as possible in a single machine. They might also spread the VMs of the same tenant across multiple servers to provide better fault tolerance. This will result in better utilization and lower operating costs for the providers. There has been many recent work on improving the hit rate of a single cache tenant. Here, our goal is to achieve optimal hit rates for several cache tenants by efficiently managing the memory of their multi-tenant environment. If multiple instances of memory caches are placed in the same machine, the common approach is to statically partition the physical memory based on some criteria. For example, based on the initial memory the customer requested or the price they pay. However, workloads are dynamic, meaning they show significant diversity in terms of working set sizes and access patterns. This would lead to a case where large cache tenants are wasting their space because they have small working sets at the time, while there are small tenants that are starving. We call that the tenant calcification problem. This issue might also occur internally. When the cache is empty, the slab classes requesting memory before others will occupy most of the memory pages. In memcached, once the page is allocated to a class, it cannot be assigned to a different class or tenant. But the popularity of slab classes might change over time. So it's very likely that there would be many underutilized pages in some slab classes, while there are classes that couldn't get the memory they need. This well-known problem is referred to as a slab calcification. So static allocations, or any allocation in general that does not take the dynamic aspects of the workloads into consideration and fails to adapt to the changes in the tenant's demands, leads to suboptimal performance. Every tenant has a different working set with unique characteristics. In a multi-tenant environment, the key to achieving optimal hit rate is to identify the working set of each tenant and allocate the memory accordingly. And if the working set change, the system should detect and adapt to those changes as soon as they happen. So what is the working set and how can we identify it? Before answering that question, we must know about the performance cliff. A performance cliff occurs when a small increase in the memory results in a drastic improvement in the hit rate of the application and vice versa. They usually happen when a working set, or at least an important part of it, fits in the cache, leading to improved locality. Finding these cliffs in the performance of an application or tenant leads us to identify the working sets as well. We can find these cliffs using shadow queues. Shadow queues are extensions to the main queue that contain the keys of evicted items in the same LRU format. If a GET request misses the main queue, but it hits the shadow queue, it means that this request would have been a hit if the main queue was larger. If we find the distance of the item from the head of the shadow queue, we can know the miss rate for any cache size larger than the current size. And then we can use these values to construct the miss ratio curve, or MRC. And then when we have the MRC, we will know the working sets. If we find the, so here the idea is that if we find the reuse distance of all missed items, we can estimate the miss rate for any cache size larger than the current size and construct the miss ratio curve. So what is the reuse distance exactly? The reuse distance is the number of unique items accessed between two consecutive accesses to the same item. And in LRU queues, it is the same as the stack distance, which is the distance of the item from the head of the queue. The LRU queues are usually made by linked lists, and the simple approach of traversing a linked list from the head until reaching the item would take of n time for a queue of size n. But this time complexity, as I will show in the next slide, is not good enough. So in our work, we had to think of an approach to make it faster. We managed to reduce it to logarithmic, or O of log n, using a balanced search tree. To give you an idea of how much in practice a logarithmic approach performs better than a simple linear method, I'm showing you the result of an experiment with it. In this experiment, we had two identical tenants, meaning both tenants had the same size and workload, and both were receiving an equal rate of requests per second. Their working set and access pattern was a large sequence that couldn't fit in a 4 GB cache, and all the requests were misses. To show the worst case, we made the tenants to find the reused instance for all the missed items, which in this case meant all the requests. The only difference was their approach for finding the reused instance. One of them used the linear approach, and the other used the logarithmic method. This figure shows the average latency of requests for both tenants over their runtime. The longer they were running in the larger was the size of the shadow queues. As you can see, the linear method or the red curve was extremely slow, causing the tenant to service significantly lower number of requests. And in some cases, it became totally unresponsive because the breaks you can see in the red curve. Whereas the logarithmic method did not suffer in performance at all. Before I discuss our work, I'm going to briefly talk about related work in our evaluations and related work that we use in our evaluations and discuss some of its limitations. The cliffhanger was proposed in NSTI 16. It tries to solve the slab calcification problem by reallocating memory from one slab class to another in the same tenant, which means the total size of the tenant would not change. Cliffhanger uses small shadow queues or one page to optimize the space within a tenant. It counts the number of hits on the shadow queue of each slab class. And once any of them reaches a certain threshold, they take a page from another class and assign that to that slab class. Cliffhanger uses small shadow queues so they can avoid the cost of reused distance calculations. But this forces them to use an approximation technique to predict the misratio curve. There are two limitations in their work. First is that they do all the reallocations internally. They limit the pool of the slabs eligible for reallocations to the same tenant. In our first work, Tingo, we removed this limitation. So the tenants could receive memory from a slab classes of other tenants, which subsequently enabled them to increase or decrease their total size. The second limitation is that Cliffhanger cannot detect those cliffs that happen far away in the hit rate curve, particularly when there is a large gap or difference between the current memory size and the size where the cliff would happen. MemSweeper does not have this limitation. We did an experiment and compared the performance of these three systems for workload that had far off cliffs. The result is shown in this hit rate over time figure. Tingo is the green and MemSweeper is the black curve. As you can see, Cliffhanger performs worse than both because of these two limitations. To solve the static allocation problem, we proposed a mechanism in MemSweeper that can reallocate the memory pages between the classes of one tenant as well as moving the pages across tenants. These reallocations are decided based on the marginal utility values that are calculated for all the shadow pages using their latest hit counters. I will explain marginal utility later, but before that, I must discuss the design of MemSweeper and its algorithm of finding the reused instance values. In MemSweeper's environment, all tenants reside in a pre-allocated shared memory. This shared memory is managed using an entity called the tracker. The tracker is the supervisor to all the tenants, and it performs all the memory allocations, reallocations, and it holds critical information needed to manage the shared memory. In implementation, to minimize the overhead, we have not made it a standalone process. It is just a single page. In addition to the shared memory that is used by the tenants for inter-process communication and coordinating actions such as reallocations. Each tenant has a preset share size from the shared memory that guarantees the availability of new pages for the tenant. By default, all tenants have an equal share. We use a POSIX shared memory. We replace the normal routine of memory allocation in Memcached, which is malloc, with the new function that uses a map to allocate the page inside the shared segment. When a tenant asks for a page, the next available page in the shared memory is mapped to the requesting tenant, as long as the tenant hasn't filled up its share. Neighboring pages might belong to different tenants, as we can see in this picture, which is also showing what would normally happen when tenants ask the operating system for a page. So how do we find the reused instances efficiently? In MemSweeper, we use an Avl tree for these calculations. Avl tree is a self-balancing tree where the difference between the heights of the left and right subtrees are not more than 1 for all the nodes. It's a binary search tree, so it's sorted. We have this Avl tree in addition to the main queue to keep track of the last access time of the items. Other than the time, the tree nodes contain the size of the right subtree as a weight attribute, which basically shows the number of their older items. So now every node knows how many items in its subtree are older than itself. To find the reused instance, we simply traverse the node toward the root and we add up the weight of the node's parent if this node is a left child. Using this method, it would take a height of the tree or log n iterations to find the reused instance. So a thread calculates these reused instance values for all the misses, and it updates the hit counters for all the shadow pages and main pages. Then it finds the marginal utility values of all the shadow pages. We define marginal utility as the per page hit gain for a continuous block in the shadow queue, or the potential hit gain from all possible additions to the main queue. You can see the pseudocode on the right. MemSweeper is the first version that we designed. Its goal is to maximize the memory utilization and overall hit rate of the system. It uses the knowledge of utility values to identify the sites of the reallocations, which we call the victor and the victim. It reallocates the page with the lowest number of hits to the tenant that would potentially gain the highest number of hits. Once the utility of a shadow page, let's say page X, reaches a certain threshold, the tenant will receive memory to the amount of the position of the page X in the shadow queue. For example, if the 100th page of the shadow queue for a tenant has the highest utility value between all tenants, this tenant is set to receive 100 pages. We find a new victim for each page, since we want these pages that would be moved to be the ones the ones with the lowest utility values in all the shared memory. So they might belong to different tenants. Exchanging a low hit underutilized page for a potentially high hit and fully utilized page would result in reallocations that would maximize the overall hit rate and utilization. But it might be unfair to some of the tenants. For example, an aggressive tenant with a high RPS or miss rate would take all the memory from others that have lower miss rate or requests per second, causing them to suffer too much. We anticipated two thresholds to control the amount of suffering that can be caused by MemSweeper. Threshold on size, that is the size that the tenant is allowed to lose, and threshold on the hit rate, that is the hit rate that the tenant is allowed to lose if it's the victim. But the efficiency of MemSweeper comes from the fact that it is affected by a single factor, which is the utility value. We improved the decision-making process to include other factors which are necessary for a fair and efficient reallocation. All these factors come together in form of a score metric. These factors include the utility value, or S0, which is from MemSweeper, number of released pages, number of gained pages, number of misses in the last second, the total size of the tenant, and also the time that has elapsed since the tenant was given a page. which means the longer a tenant has waited for extra pages, the higher would be its chance of receiving one. Fair MemSweeper would reallocate memory from the tenant with the lowest main queue score to the tenant with the highest shadow queue score. The amount of memory is determined by the marginal utility value. Next, I will discuss the evaluation of MemSweeper. So we implemented all the MemSweeper variants, including Fair MemSweeper, Max MemSweeper with 2 threshold on top of Memcached, and we compared them against base Memcached and Cliffhanger's hill climbing implementation. For our testbed, we used physical servers on Cloud Lab, whose specs are shown in the slide, and Cloud Suite. Cloud Suite is a benchmarking tool, and it provides a pre-built Twitter dataset that we scaled to different sizes for our benchmarks. The working set size of all tenants are shown in this table. The Cloud Suite could only simulate a random access pattern. So in order to create more diverse workloads, we did some modifications to the Cloud Suite client and enabled it to create additional access patterns like sequential and also their combination. Additionally, we use the simulated workload from Facebook or etc. for one of our workloads. So in each of these categories, we ran 11 benchmarks, and in each of these benchmarks, we used 4 tenants sharing a 16 gigabyte shared memory. One of the tenants was designated as the demanding tenant, which is the tenant 3 in the table. All tenants had an equal share of a quarter of the total size initially. We ran the benchmarks, let the system adjust the memory allocations of the tenants, and record the changes in their memory size and hit rates until they reach the steady state. I will just show the results for one of the workloads. This is the final hit rate of the depending tenant in all 11 workloads of the random sequential combination. As you can see, both Memcached, both base Memcached and Cliffhanger cannot detect the demand changes and far off cliffs and fail to adapt the tenant to its working set and improve the hit rate. Whereas all MemSweeper variants, except the Max MemSweeper with the threshold on size, they can detect such changes and improve the performance. The size threshold was set to a number that was not high enough to find a cliff, so it resulted in a lower hit rate. This is the overall hit rate of the system for the same workload. A similar behavior can be seen here. Base Memcached and Cliffhanger perform worse than the others because of their failure to adapt the demanding tenant to its working set and increase the memory size, whereas all MemSweeper variants, except the size threshold, could change the allocations and improve the performance. This is the summarized results for all the workloads. It shows the average miss rate reduction of MemSweeper variants. As you can see, in the random workload, Fair MemSweeper performs the best, but in the sequential workload, Max MemSweeper has the highest miss rate reduction. These are the other 2 categories. Again, Max MemSweeper performs the best and has the highest miss rate reduction for both workloads. Based on this result, you may think that Max MemSweeper is the obvious winner in terms of utilization and hit rate. However, we will argue that it is not fair toward the victim tenants. We did an experiment on Max and Fair MemSweeper to show how they handle a very aggressive tenant. Our hypothesis was that approaches like Max MemSweeper that aim to maximize the utilization, they favor aggressive tenants, unlike Fair MemSweeper. Here we define the aggressiveness as receiving double requests per second. In this experiment, we had 2 tenants, sharing an 8 GB memory. One tenant received 20K requests per second, and the other received 10K requests per second. We use the combination workload with a performance cliff happening before the size 6 GB. This figure shows the memory allocation of both tenants over time. The blue curve demonstrates the performance of MemSweeper, and red represents the max version. As you can see, the max version has significant fluctuations because of the difference in the request per second and utility values, whereas fair version was not affected by these differences. This is their hit rate over time. If you look at the blue curves, it's clear that using MemSweeper, both tenants ended up with a similar hit rate. But in the max version, there is a huge gap between the two, only because of the difference in their request rate. This wouldn't happen in a firm mechanism. So we think that in environments in which fairness is a priority, for example, multi-tenant cloud, MemSweeper is the best option. But in those aiming to maximize utilization, max version might be the better choice. That is all, and thank you all for listening. I would be happy to take any questions.
Very good. Thanks, Amiri.
Sure.
So, Amiri, I like the topic, and thank you for submitting the paper to ISMM. That the system design evaluations excellent. I have a paper actually in the past solving a similar problem. I'm going to share a paper link at the Slack channel. But let me see if there's any question online for you. Shai Bergman has a quick question. I'm just going to read. Memcached page size are 1 megabytes by default, but memory now is shared between different Memcached tenants. Wouldn't make more sense to share memory with 2 megabyte pages? This will cut down the tail latencies due to TLB misses and less allocation mapping overheads. And since the 511 plus 1 page table updates at the last level, question mark?
So the thing is that we did not consider the tail latencies in our evaluations, but about sharing the memory with 2 megabyte pages, I'm not sure how that can help because in the having the granularity of the page reallocation to just 1 megabyte would save us from additional and unnecessary reallocations in the future, because it's possible that 2 megabyte reallocating 2 megabyte would hurt the performance of the victims more than it should. So the victim might request the memory back in the future. So yeah.
Excellent. One more question from Jeremy. Did you consider other optimization techniques for resizing? It looks like you used an analytical model, handcrafted heuristic. What else might be appropriate? Mathematical optimization like integer linear programming, or meta heuristics like particle swarm optimization, or a deep learning model? in general, cache optimization is certainly a complex problem.
It is, but I'm not sure I understand the questions, because we did not use other like optimization techniques. We're just trying to adjust the memory size of the tenants in a multi-tenant environment. So the hit rate, the overall hit rate of the system is improved. I'm not sure if I quite understand the question. I will try to answer it offline. So.
Yeah. Good idea.
Yeah.
All right. Thank you, Amiri.
Sure. Thank you.
Okay. Coming up, we have our second paper, replication-based